My name is Hannah. I'm a PhD candidate at the University of California, Riverside, and today I will be talking about MaTCH, which stands for Microplastics and Trash Cleaning and Harmonization, a semantic data ingestion and harmonization tool using AI. So first, let's dig into the current state of plastic pollution. In a newly published study by Hartman et al. That was just came out a few weeks ago, actually, authors suggest that the volume of literature that exists on microplastics, currently in the tens of thousands, has already exceeded the research community's capacity to effectively synthesize and mobilize these data into useful information, something I think maybe we've all been feeling slowly building up over time. So this is due in part to the sheer number of studies that exist, but also due to a lack of standardization in methodologies and terminologies used across studies. So while new studies should certainly focus on integrative structuring and open data sharing with such a huge volume of knowledge existing already, some work on harmonization, so just being able to translate between these studies is warranted. And today we ask, what if AI could assist in this translation? So what makes plastic pollution studies so difficult to synthesize? As a particulate contaminant, they consist of a diverse suite of different material types, shapes, colors, sources, and sizes. So data sets on plastic particles are uniquely complex whenever the particles are fully characterized. This is true of both micro and macroplastics, as you can see illustrated with the little example on screen. So the difficulty of data management for a diverse contaminant suite is then, further exacerbated by this lack of standardization. So this stems from the variations in possible methodologies studies can use to characterize or chemically confirm plastic particles. So this includes, but is not limited to, particle level data sets that identify and manually characterize particles versus concentration level information only. Quantifying particles by a mass, typically by a count versus by a mass. So this is typically by way of using some sort of vibrational spectroscopy like barometer FTIR versus a mass-based identification technique like PI-GCMS. In addition to differences in the instrument type used, the identified material types can also vary depending on the reference libraries used to identify spectra, even if you are using the same analytical techniques. Lastly, concentration values are not comparable whenever there are differences in the size ranges of particles being analyzed. So as you can see with the little example on screen, the exponential growth in the number of particles as you decrease in particle size makes direct comparisons of concentrations across studies with non-harmonious size ranges inaccurate and misleading. So in an attempt to help remedy this, we developed an open source R-Shiny web tool called MaTCH to integrate various data harmonization steps together in a single automated algorithm. So this includes integrating some previously published yet often underutilized harmonization methodologies like particle size rescaling techniques and converting particles from a count to a volume and then lastly to a mass. And what I'll be mainly focusing on today is the framework that we developed for the issue of non-harmonized terminology, so dealing with the categorical variables that get input. So this framework was developed by first assessing the current terminology used in the literature. We looked at around 60 different microplastic studies from different environmental compartments. And then we recorded the terms that they used to describe material and morphology types, and then sorted them in two simple ways. So first we related synonymous terms as shown here with the different ways of denoting polyethylene. Second, we related terms hierarchically, as you can see here, with high density and low density polyethylene being the child term to polyethylene. But what if a term doesn't relate to anything known in our database? So this brings us to the AI component of this tool. We utilize an embedding model to relate outside terms to known terms within our structured database. Embedding models are a specialized type of machine learning model that's able to take unstructured data, in our case, this is just words, language, and turn them into a vector. These vectors can then be related in what we call embedding space and assessed for their similarity. In this instance, we use the text embedding ADA2 model from OpenAI, which gave us a matching accuracy between 71 and 94%. Why use an embedding model? There are some upsides. They're cheaper, faster, and less energy consumptive generally than LLMs or other generative AI models. They're also not as prone to hallucinations in the same way as generative models would be. And this is because their outputs are largely deterministic, where deterministic just means that a fixed predictable outcome that are produced from the same set of initial conditions, making them more easy to audit over time. Also, however, note that I do say largely deterministic in this case. So while embedding models themselves are deterministic in their design, third-party API models like the one we got from OpenAI are subject to some slight drift over time due to like different model updates or infrastructure changes on OpenAI's end or whatever company you're getting it from. So this is one of the trade-offs using an open source model instead of a locally hosted one. You get it's very convenient and better performance of these large generalized models, but you lose some control over long-term reproducibility. But with that being said, the changes are quite small, just a slight drift over time, and then these larger updates come typically in the form of new model releases. So this contrasts with stochastic models like LLMs, which explicitly do account for random variance using a temperature parameter, meaning they do have probabilistic outcomes. So they're not strictly reproducible, but deterministic models are also more limited in their application than the stochastic models, which are able to perform sort of advanced reasoning, which is obviously crucial and very much needed in some applications. So the takeaway here is just that, not that any one model is really better than the other, but just that, we don't always need to reach for the most powerful tool on the shelf, depending on the application. And for ours, the embedding model works just fine and sped up our processing time and lowered cost. On that same note, I think another point worth highlighting here is that our application of AI on this project is just a small part in a larger data harmonization workflow. This two-stage pipeline where terms are matched to our human-designed relational table database and then passed to the embedding model as a fail-safe allows the AI to more so just extend the reach of our work rather than totally replacing anything, which I think is going to be the case with most of the talks today. So as you can see here on the flowchart outlining the algorithm steps in MaTCH, the semantic harmonization step provides us with the foundation to be able to apply these other really great data harmonization techniques developed in other work to more rapidly and also to larger data sets. So this includes matching harmonized material types to known polymer densities, using harmonized morphology terms to route our data to the best possible equations to estimate particle mass, which can then be combined with density to estimate mass. Lastly, this wasn't as focused on so far in this talk, but we can also use the material morphology information from trash data sets to estimate a mass for them as well, because they have their own relational table database mirroring the microplastics one, and we have mass estimates for some of those items as well. So now I'll transition into a short demo of the tool itself and go over a quick use case. So in our next talk, we will be hearing from Dr. Wayne Calger about OpenSpecE, which is an open source spectral identification library and software. If you were to input a spectral map into OpenSpecE, your output would consist of particle level data, where each particle has an identified material type and various particle shape factors. So if you go over to MaTCH, the tool itself is just a screen grab at the homepage. You can then take this file staying on the homepage, just label MaTCH tool, and then the data format tab that is labeled microplastic particle, and then just drag and drop it into the CSV file. And then MaTCH will first harmonize all of the material terms, allowing for users to override any matches made by the AI, which you can see in this little drop-down menu here. If you think it didn't match it correctly on the first try. Second, it will then match these material terms to a database of polymer densities that we have curated. A lot of them were from this MatWeb website. You can also, I'll reference the publication on this at the end, and then you can visit it to get the full breadth of where we got these density measurements from. But yeah, there was like over 70,000 different density measurements for 300 unique material types. And then we just took like averages and percentiles from those distributions. And then third, it will analyze what shape factors were provided and choose the best possible particle volume equation. So in this case, where there is no morphology type that was manually identified, but we do have the perimeter of the particle along with the long and short axis. The equation by Barchesi et al. 2023 was found to be the most accurate at estimating volume. However, in other scenarios where perhaps perimeter wasn't provided, then there's a whole decision tree that goes into. And then fourth, we combine this density information and the volume to estimate particle mass, where MaTCH will also provide these like quick visualizations. These are sunburst plots, so just like the hierarchical pie charts basically in this drop-down menu, so you can just rapidly compare the proportion of different material types on the basis of count versus as a mass. So all this data is put into CSV file that you can download here at the top of the page. And this is just one of the many different use cases for the tool. So if you're curious about what different data cleaning functions can be performed with a given data set, you can click on this template tab in the corner and then select the type of data that you have, so particle level versus concentration, and then all the characteristics you have about the sample. And this will also give you a little downloadable CSV to show you how the structure should look like, column headings and all that. So for more information, you can check out the publication that we wrote on this tool. It's an ES&T. So this includes the model validation and some like different proof of concept examples. So zooming back out from MaTCH, I'm really looking forward to hearing from all of our different speakers today to hear how everyone has begun to apply AI to your research to speed up these small and time-consuming tasks. So yeah, with that being said, I would like to thank my collaborators and funders on this project. Feel free to scan the QR code here if you'd like to check out the tool, and I will take any questions.